Welcome to the third installment in the Collab Ed chemistry course on YouTube. So today's video, I didn't state it in the previous one, but today's going to be kind of a part 2 for the previous video that was on the base SI units and unit conversions. So today I'm going to go more in depth on prefixes and sig figs, and I'm also going to, at the beginning, I'm going to briefly review what we did in the last video. So in the last video, we talked about the 7 base SI units right here, and we have, their length, mass, time, temperature, and sorry, let me complete that so it doesn't look like they're two separate letters. And amount of substance, or the mole. So that's 1, 2, 3, 4, 5. And then we have the two others, the amp and the luminosity. But for the sakes of chemistry, they're not super important. So the base unit for length is the meter. The base unit for mass is the kilogram. The base unit for time is the second. The base unit for temperature is Kelvin. And the base unit for substance is the mole. And of these, the most important for chemistry is probably the mole. And if you remember, the mole is a way to describe amount, just like how a dozen is a word for 12. The mole is a word for 6.02 times 10 to the 23 pieces of something. And we usually use that for counting atoms. And this number is called Avogadro's constant, and it comes from the amount of atoms found within 12 grams of carbon-12, or 12,6 carbon. 12 is the atomic mass for carbon, meaning it has 12, and the 6 is the atomic number, so 6 protons, and subtracting 6 from 12 means 6 neutrons. So this isotope of carbon has 6 neutrons, 6 protons, so it has a mass of 12. And within that exact mass of 12 grams, there's 6.02 times 10 to the 23 atoms. Now, that's a brief overview of what we did last time. Unit conversions are also fairly simple. They're simply a way of, so say you have 1 milliliter over here, and you want to turn it into a liter. Well, all you have to think of this unit as something being equal to 1. So in order to get rid of it, you would have to put it on the bottom of you'd have to multiply it as a denominator, right? And if you want to turn this into liters, you would have to put liters on top in order to get the result. So for every liter, how many milliliters are there? Well, there are 1,000, or 10 to the 3. And for liters, that's just 1. So for every 1 liter, there's 10 to the 3 milliliters. So if we have 1 milliliter, divide that by 1,000, and we get 0.001 liters. And there you go. That's our brief. That's I said that a couple of minutes ago, but yes, that's our actual summary of last time. Now today I'm going to be talking about the prefixes right here, and for the cases of chemistry, we're going to be talking about 6 different prefixes. Let's start with in the middle we have 10 to the power of 1, right? That's equal to 1. 10 to the power of 2, that's, sorry, let me, excuse me. Sorry, I'm kind of stuttering all over my words, but 10 to the power of 0 is 1. 10 to the power of 1 is 10. 10 to the power of negative 1 is 0.1. Now, building off of this, what we can do, what I'm going to now do is write a bunch of different 10 to the power of numbers, and I'll tell you what each of what the prefix for each of them is, and why it's useful. So we start with the most common one, 10 to the 3, which is 1,000, and we write that as kilo. And then we have 10 to the negative 1, which is 1/10, and we call that deci. Then we have 10 to the negative 2, and that is 100th, so therefore we call it centi. Then we have 10 to the negative 3, that is 1,000th, so therefore it's milli. And then now we take go jumps of 3, so that we go 1,000, a million, a billion, trillion, and so on. So, but for now I'm only going to do two more jumps of 3. So 10 to the negative 6 is a millionth of something, and that's called micro. And 10 to the negative 9 is a billionth, and that's nano. And now if we go to positive ones above kilo, 10 to the 6 is mega, and 10 to the 9 is giga. You might recognize mega and giga from your flash drive storage, so megabytes, gigabytes. And then, those are all the prefixes, and those are powers of 10. So usually in chemistry, we usually just use scientific notation, which is just a power of something that's within the power of 1, from 1 to 10. So something like 3 times 10 to the power of whatever it is you have up here. And so sometimes we might use these prefixes instead of using this scientific notation. It's all up to the user, whichever you think is easier. And it's all about just kind of counting your zeros, counting your places after the first number in whatever you have measured or whatever you've calculated. So let me clear my screen. And now we will move on to significant figures, which are how we record a certain amount of digits. So let's say we have a ruler, right? And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. And say this ruler is a very, very not precise ruler. So it only has halfway points marked. Now, when you're talking about a ruler that has not a super specific amount of points, so let's say we have an object that is this long. Let's say it's a pencil or something. So you see that, so with confidence you can say that it reaches 1, 2, 3, 4, 5, 6 inches, right? Sorry, I shouldn't be using inches. This is not good. In a science class, we should always use centimeters. So let's say this is a 12 centimeter ruler. So you can say with confidence, you can see that it lies somewhere in between 6 and 7. So that is 6 point something, for sure. Now, the next step, you can say with confidence it lies maybe from 0.5 to 0.7. So like slightly above 0.5. So now you can write the 0.5. However, the ruler doesn't get any more specific than that. So you can't really say what happens after this or whatever. Sorry, I wrote a 6. And that is where significant figures come in. Significant figures means all of the numbers that are relevant, that are accurately measured, plus one estimated number. So this looks like it's barely over 0.5, so I'm going to put 6.51, and that's where I have to stop. That's where I have to stop, because that is the only, I can only get up to this amount, and this measurement is what stops me from becoming any more specific, because you just can't know. The ruler isn't precise enough. So we say that this number has 3 significant figures because it has 3 numbers that are actually contributing to whatever you're measuring. So significant figures have 5 rules. 1, 2, 3, 4, 5. So number 1, all non-zeros count as sig figs. Then second is zeros before the first non-zero count. Zeros between, there we go, between non-zeros count. And then number 4, zeros after a non-zero but before decimals. Must have a decimal to count. Decimal to count. I'm running out of space, but that's just count, okay? Bear with me. And then finally, zeros after the first non-zero. Zeros after the first non-zero after the decimal always count. Excuse that last part. I'm running out of space. So if you want right now, you can like screenshot these rules, because I'm about to clear it and I'm about to go more in depth about what these rules mean. I don't have a lot of time because I want to stay below 15-16 minutes, so I'm going to try to quickly explain why these rules are relevant. So hopefully you screenshot it or something. So let me clear my screen. So let's say we have 60.4050. Okay, let's go over the first rule. All non-zeros count. And this is pretty understandable, right? They are something that is, they're values that mean that are not nothing, so obviously they have to count. The second rule says zeros before the first zero do not count. So if I wrote a 0 here, if I wrote zeros there, you can understand again, hey, that doesn't make sense, that's unnecessary, they're not significant. So we can take that away as well. Zeros between non-zeros count. Again, this also makes much more sense because you can see 60.4 would not be the same without this 0 in between. 60.405 would not be the same without this 0 either. So Now, this is where it gets a little bit more tricky, but I'll try to explain these rules as simply as possible. So zeros after a non-zero, but before decimals must have a decimal to count. So let me do a new number. If we have this, right? We are saying that basically these two zeros are insignificant unless they have a point right here. If once you write that point, it's significant, because sometimes you just can't be sure what those zeros mean without clarifying that there is a decimal right there. So even rule number 4 is fairly simple, and number 5 says zeros after the first non-zero after the decimal always count. So this decimal does count. And if I wrote more, these two also count. And you might be wondering why. This is because, remember how I talked about precision, and you can only estimate after you are sure where the ruler stops. So let's just put 5 points. So might make these intervals smaller and smaller. So say I have an object about this long. Well, you can say that, hey, I know for sure it goes up to here. I also know for sure that it goes up to here. And say you have even tinier intervals right there, and it doesn't even go past this first interval, so you can say with confidence, hey, it also goes up to here, which means that you can write, now if these are all at a 0 point, that means you can write a lot more zeros in, and you are confident that those are 0. After those zeros is where you might write like a 3 or a 2 as a guess to where the object stops on the ruler. So hopefully that makes sense, and hopefully I could explain sig figs in a simple way that helps you to understand why they're important and why they're actually used. And in the next part, I will again go more in depth, just to really try to ingrain the ideas of sig figs, and also I will talk about multiplying and adding sig figs as well. So thank you for watching. If you liked it, be sure to comment, like, and subscribe, and I'll see you on the next one. Bye.